Hi, so thank you very much for allowing me to do this virtually on behalf of Eloisa, Shabir, and Melpi. So what we've got in many algorithms is that we know that there is correlations between features, but we don't always use them. So methods such as random forest and others, they tend to use individual features to decide on how to split the data for classification and regression. The issue with this is that once we try to learn about this and about biomedical discovery, we won't be able to accurately tell what's actually going on. So earlier this year, we published a method called LavaSet, which tries to incorporate latent features to not just do the splitting on one feature, but do that on a combined set of features. And we've demonstrated that method previously on 3 different types of data. Spectral data, as well as temporal data, as you can see in the middle, the ECG data, as well as 3D imaging. What we found is that this type of approach is better able to give sort of correlated features the same importance as they would compare to the other methods. So what we found is that it had non-inferior performance to random forests. And our code was completely written in Python, or exactly in C++ with a Python wrapper there. So it's really quick. And the things that people need to do is you need to supply some distances to know how to connect those features up. But one of the limitations still is that the feature importance was still based in the non-negative domain. So basically positive values like the Gini coefficient. So that's what we set to improve here, and that's what I'm mainly going to talk about now today. What we want to know is if we have an important feature, to what class is it contributing, and is it contributing positively or negatively? So we are using something called the G-test, or a modification of it, and G-test is similar to the Kullback-Leibler divergence, where we're comparing frequencies of categorical data. Now, the good thing is in ensemble methods, we do have those categories, simply going left, going right. And what we've done is we've developed these partial G-tests where we look at it per class. How is that split caused the nodes to be more pure in a sense? And this original equation there, we've replaced that expected level of frequencies by half of what the parent is. Now, the parent node is essentially the amount of data that comes in. Right at the start of a single decision tree, we have 2 things. We have the ancestor, which is all the data that comes in, and the parent node being at that point the same thing. Then we start splitting. If we'd have a perfect split, we'd have 2 times the parent times natural log 2 there. The further down we get into the tree, we need to know how important is it, so how many samples are left. And that's when the parent and the ancestor change. So the parent will change, the ancestor will always be the same, and that's how we normalize. The main thing that we look at is between these 2 left and right values, we can look at the difference in them, and that sign tells us about the directionality. And this is how we've developed the class-based integrated directional feature importance. Eloisa came up with the name, or CLIFFE. And the equation on the left is basically what we need is what you see on the right-hand side of the screen to be able to calculate it for each class. So suppose we have this split where one class is split more or less equally, and another class is split mostly on one side, in this case towards the left. You can see that there's 2 CLIFFE values that we calculate, and one of them is large for the class 1 because that's split better, and the other one is very close to 0, so not really important. And the same happens throughout, and you'll see that as we make these consecutive cuts, the CLIFFE value is interpretable and also scaled. And simply what you do across the entire model, you just sum all of these values for the variables and you get the importance. So what the data that we used and what I'm going to show you today is proteomics data from the TCGA. And what we've looked at is 28 different cancer types, and we have about 7,800 samples and 113 proteins. And the input data for the LAVA methods is we've looked at the protein-protein interactions. We compiled that from StringDB with a variety of different measures to determine whether or not 2 things should be combined in their analysis. So I'll go over this very quickly. but you'll be able to have a look at this as well. One of the ways to very quickly show the benefit of the method is using some very common data, the iris data that I hope for many of you have seen before. And you'll be able to see that on the left-hand side, the Gini value, you see clearly some variables are more important. We've also added some noise there. And the Cliffy value has some more extreme values if we look at it overall. Now, the real interesting thing is when we look at it per class, where we can very clearly see how the decisions are made for each of the important variables. We get the complete opposite when we break that. So when we just permute the labels, everything is broken. The Gini will still show us important values, but the Cliffy now is very much centered around 0, and there's not really any differences between them. Now, for the more interesting data, what we did is we had about 100 randomizations of the trained test split, and we evaluated the models all throughout. So in this case, the LavaSet model is slightly quicker than random forest, with the random forest slightly outperforming it, but they're very, very similar. The real benefit is the interpretation of the features, which in LavaSet, because we combine these features, it makes it a lot more easy to understand these type of mechanisms, especially with connected proteins. So we did a few different things. One of the things you can see on the right-hand side is we're plotting the top few features, which are connected, and you can see in the bottom two, C and D, for uterine cancers and prostate cancers. Certain markers, you see the top features are slightly different, but there's two that are quite common between both of them, but they have quite opposite signs between them. And that's something interesting to explore, because the same features, they are connected, but they behave completely differently. Now, we looked at these top features, whether they're really important. In an ablation study, we got rid of the top set of features and saw that the performance indeed drops. Likewise, when we remove the least important features, the one with the lowest Cliffy values, the model tends to improve a little bit, even by getting rid of the noise. So similar to recursive feature elimination. Now, the benefit of Cliffy is we're able to look at individual features across all of the classes to really easily see where is this feature importance for. So if we look at the ER alpha again, we can see that the ovarian and uterine cancers have much higher values, and other cancers such as prostate, they have lower values as well. And you see that same pattern throughout different ones. For comparison, on the right, you have a protein that's not important at all, and everything is really around 0. Now, why is this useful? Is because actually, if we look at one of them, in this case, MyH11, can see that these Cliffy values really well approximate what actually the raw data also tells us. But bear in mind that the Cliffy is not calculated on the entire data, but just on these subsets we use to make decisions. Compared to the Shep value, both Cliffy and Shep are able to identify those important features, but Cliffy is the one that really well matches the original data, and that's basically a benefit for the interpretation. And so just in conclusion, one of the things that we found is quite a lot of these proteins that we associate with different cancers using these methods are indeed reported before, and that gives us confidence that that metric can indeed pick up real things. And interestingly, even though ER alpha was reported in prostate cancer before, MyH11 has not. So in conclusion, this method is integrated within the algorithm, so you don't need to do this after the model's finished, such as you need to do with Shep. It's quite interpretable, and we implement it within the existing LavaSet package. And yesterday, the paper is online, so for those people who want to look at that, they can have a look at that paper. And some of the things that we're doing in our on our lab now in my group is also looking at other types of information. You can see on the right-hand side on metabolic reaction networks that we're trying to compare against other topological methods. So I'll leave it at that for people who want to read a lot more than I could say in the last 10, 11 minutes. Either scan the QR code or have a look on online for the paper. Happy to take any questions if there are any.
Thank you very much.